In 1856, someone proved the exact reason our planet is warming using nothing but glass tubes and sunlight. Then history erased them. For over 150 years, the world credited someone else. It began with a question nobody could answer. Why is a mountaintop closer to the sun so much colder than the valley below? It all started like this.
If you stand on a mountain peak, you are physically closer to the sun than someone standing in the valley below. Logically, you should be warmer, but you're freezing, and they're perfectly comfortable. In the 1850s, this simple paradox puzzled the scientific community. To explain the temperature gap, researchers split into two camps. One group argued that the specific angle of the sun's rays striking the Earth at different elevations caused the difference. The other side argued it had to do with the density of the air itself. For years, these men debated the issue in academic journals. They traded theories and published strongly worded opinions, but nobody actually ran a physical experiment to see which idea held up to scrutiny. Eunice Newton Foote read these debates. Thanks to a rare and rigorous scientific education at the Troy Female Seminary, she was trained to value empirical data over abstract theory. She decided to settle the argument by testing it. To solve a mystery spanning miles of open atmosphere, Foote realized she needed to shrink the sky. She had to isolate the variables in a controlled, tabletop environment where they could actually be measured. Her physical setup was elegantly simple. She took two identical glass cylinders, each about 4 inches wide and 30 inches long, to act as her contained environments. Inside each cylinder, she placed a mercury thermometer. As you can see on this vintage 19th century instrument, the spiral-shaped bulb at the bottom maximizes the surface area exposed to the gas, allowing the mercury to expand and accurately register on the scale above. This diagram shows the core logic of her control. By placing both cylinders side by side in the exact same sunlight, the solar input is identical. Any difference in the output temperature has to be caused by the single isolated variable, the gas trapped inside. For her first test, she isolated air density. Using a hand pump, she pushed extra air into one cylinder to compress it and vacuumed air out of the second. When placed in the sun, the thermometer in the dense compressed air climbed higher than the one in the thin air. That result settled the academic debate. Valleys are warmer because the air settling in them is denser than the thin air on a mountain peak. But more importantly, the test proved Foote's physical apparatus worked. She could reliably measure how different atmospheric conditions reacted to solar heat. Next, she swapped the variable from density to moisture. She prepared one cylinder with completely dry air and filled the other with damp, humid air. The damp air heated up noticeably more than the dry air. Then she tested chemical composition. She filled the first cylinder with common atmospheric air. Into the second, she pumped what they called carbonic acid gas, known today as carbon dioxide. This graph plots the temperature of those gases over time. When she placed both cylinders in the sun, the temperature of the carbon dioxide shot up, reaching a blistering 125 degrees Fahrenheit and far outpacing the common air. Foote took the experiment a step further. She moved both cylinders out of the direct sunlight and placed them in the shade to monitor their cooling rates. Looking at the downward trajectory, the carbon dioxide has a noticeably gentler slope. It took significantly longer to return to room temperature. The data revealed a specific physical mechanic. Carbon dioxide rapidly absorbed solar heat and stubbornly held on to that thermal energy, resisting the cooling process. Foote took the data from her tabletop and applied it to the planet. She reasoned that the thin layer of atmosphere wrapping the Earth acts exactly like the glass cylinders in her lab. In her 1856 paper, she wrote out the logical conclusion. She stated that an atmosphere of that gas would give our Earth a high temperature. If at any point in geological history, the air had mixed with a larger proportion of carbon dioxide, an increased temperature must have necessarily resulted. From a modern physics standpoint, her setup had a technical limitation. Direct sunlight is shortwave solar radiation. Her thermometers were actually measuring how that incoming shortwave light heated the glass and the gas inside, rather than the true greenhouse effect. The precise mechanism was confirmed 3 years later by the Irish physicist John Tyndall. He demonstrated that greenhouse gases trap the invisible long-wave infrared radiation that the Earth's surface re-emits after being warmed. Tyndall had access to a sophisticated spectrophotometer designed specifically to measure those invisible infrared waves. But even though she was using standard thermometers, Foote's logical framework was entirely accurate in identifying carbon dioxide and water vapor as the primary drivers of atmospheric heat. Her paper fell into obscurity for over 150 years, yet her experiment stands on its own. It proves that the mechanics of global warming are not abstract outputs from modern computer models. They are observable physical realities, mapped out in an 1856 home lab using nothing more than a hand pump, glass tubes, and the heat of the sun.
If history nearly forgot me once, don't let it happen to stories like mine again. Hit like, subscribe, and help me stay remembered. Still have questions about my story? I read every comment, so leave yours below. I'd love to answer.